Okay, TSM 363, AC electric motor selection and protection. In this slide presentation, we'll talk about how do we select a motor effectively, and then what are the components, the circuit components really that we need to incorporate into the circuit to meet NEC 430 protection requirements. So we're going to look at motor selection, horsepower rating, starting torque, and housing. Then we're going to turn to protection circuit, the equipment, the devices that go into the circuit. And here we have a bunch of things. We have our disconnect. We have our circuit breaker or fuse. We have our conductors, right? The things that connect all these components to each other. We have our controller, operator, the device that turns the motor on and off. And then we have our overloads. These are all included and required in NEC 430. Spells out the horsepower and the current ratings for each of these components that we need to allow for and design around. Then we're going to finish with some NEC tables that will help us identify the horsepower and the currents that we need for each of these devices. So first, looking at motor selection, there's three main criteria that we need to consider for an effective solution. Effective solution means we're maximizing our criteria, right? If you've taken 115 with me, we talk about effective being something that maximizes our goals, our criteria, stays within our constraints. So we need to think about, is the motor able to drive the load without being overloaded? We talk about horsepower when we talk about this part of it. We have a load, we turn it on, it's running. Is the motor doing all it can and barely keeping up? If that's the case, it's probably undersized, right? We want to consider what's the full load torque, and can we meet that torque with our horsepower rating? Then we have, can we reliably start a load? The starting torque, right? What torque do we need to overcome? What inertia, what load torque do we need to overcome just to get that load to move? And then what type of environment do we need to be able to withstand? We talk about the housing of the motor. There are two symptoms that identify if we have an inefficient solution or an inefficient motor. If we're running the motor at full load torque and the slip is less than or equal to 2%, most likely our motor is undersized. Okay? Now remember, no load torque is 0.5% slip, but that's no load. The assumption is we're running under full load, and if we're in that situation and our slip is less than or equal to 2%, the motor's too small. Additionally, if we're running at full load torque and our motor current, the current we measure running through the conductors to the motor, is significantly larger than the current full load current of that motor, then there's a problem. Okay? Significantly larger, what does this mean? Some people will say 150%. It's a little bit ambiguous. We could put 150% as a number. If we're much more than 150% of our full load current as we're running that motor, something's wrong. Okay, this is not locked rotor current. This is not current spikes, inrush current. This is continuous as it's running at full load. So those are two important things to be considering that identify if we have an inefficient or ineffective solution. So let's look at motor horsepower ratings. So there's three options for selecting a horsepower for a motor. The first option is use the manufacturer's recommended per the application. We can call them, we can talk to an applications engineer, we can look at their technical documentation. Right? If we're buying a piece of machinery from a manufacturer, either they're going to have the motor installed or they're going to tell us what type of motor to use to replace one that goes bad in the event that we don't have the nameplate. Okay, so the manufacturer could be a first point of reference. Next, we could just calculate horsepower per the load application using physics or statics, or actually going out to the application and measuring the horsepower or the torque needed to move that load. Okay? We can also reference some tables and rules of thumb, and for this, draw your attention to our textbook. Appendix A and B has some very clear and very applicable tables for identifying horsepower for ag applications. There's also a link in the Week 10 lecture notes that talks about the manufacturing applications, and I'll show you that one when we get to Blackboard. But here are some references that we can use to give us generic or common horsepowers for different types of applications. So we need to consider all these things, right? Identify first, what's the horsepower of the motor we want? 3 areas we can go to get that answer. Then we need to talk about the starting torque of the motor, right? How do we get the motor to start? Do we have enough torque to get that thing spinning? So again, we can reference the textbook table 10.2. This has typical load starting ability in column 3 of that table, and it shows us, high, medium, low for different types of motors, 3-phase and single-phase motors. The subnote kind of clarifies what a high, medium, or low is as far as percent locked rotor torque. And so the locked rotor torque is another word for starting torque. Locked rotor torque, starting torque, they mean the same thing to me. Okay? The torque we need to overcome to get the shaft to move, either from a dead stop or if it stops, to get it started again. We also want to look at and be comfortable with the torque speed curves in our textbook. Okay, and of course, looking at that, when we looked at that in lecture, we have torque on the x-axis, speed on the y-axis, and these are all in percent speeds and percent torques. Okay, and we have our 100% full load relates to about a 96% full speed. And then we have our breakdown point and our locked rotor point. And those are going to be different based on the different types of motors. This is a 3-phase speed torque curve. Okay? There's other torque curves, speed torque curves for the single-phase types of motors that we can reference in the textbook. But these 2 steps, when we want to select to make sure we have the right locked rotor or starting torque capability of our motor. After we select the horsepower, this step here, the starting torque, really looks at what type of motor. Each type of motor has a different ability to have a different percentage locked rotor torque. So that's when we need to decide, do we want a squirrel cage, do we want a split capacitor, do we want induction, what do we want? Okay. Lastly, when we're talking about the motors, we want to consider the housing, the environment that we're going to be putting this motor into. What should our motor be able to protect itself from? Okay. If we look at table 10.7 in the text, there is some considerations for bearings, what kind of bearings we want. That's kind of a subjective table. It just has pros and cons of different types of bearing materials, but something we want to consider. We also want to understand how is the motor going to be mounted. There's a flange mount is common, or foot mount is common. And a flange mount, it's almost like an end mount where we have our fasteners that go straight in to the face, versus foot mount, our fasteners either come in from the bottom or down from the top in some type of foot configuration. We also want to look at, even more importantly possibly, the enclosure type. And there's common enclosure types. Open enclosure, where air flows in and out. We can see into it. We can see, to some degree, the windings internally. There's also open drip proof. Okay, so it's open, but we can't drip water into it. Totally enclosed, air over. Okay, totally enclosed, fan cooled. And then maybe one of special note, hazardous location, explosion proof, intrinsically safe areas that we have explosive environments. We want to be very careful the type of motor that we put in those environments. But there's all different types here. If we look at Granger, Granger has a very nice filtering system to filter through different characteristics of the motor we want to select. And we can look at horsepower, RPM range, voltage, motor applications, frames, phase, right? We can do all these things. And we can just kind of pull the drop downs and click the type of things we want. and it will filter to the motors that they offer in those types. So when we get to Blackboard again, we'll show you this in a little bit more detail. So these are the considerations we want to have when we look at the housing, the mechanical housing of our motor. So now we're going to turn over to the protection circuit. So the things from the NEC 430, there's 5 circuit elements that we need to be considering. The first one is our disconnect means. And this commonly is a disconnect switch, something we can just turn power off to the motor. Then we have our short circuit protection device. This is our fuse or our circuit breaker. This is the thing that if there's a short circuit, it trips or it blows. Then there's the motor controller, the device that turns the motor on and off. And then there's a motor overload protection. This is the overload relay or the heaters. These are the elements that sense the current going to the motor, and if there's too much current going to the motor, it stops the motor so it doesn't burn itself up. And then lastly, but really we can't forget the conductors. So there's motor circuit conductors. And this is going to go back to chapter 5 where we do the ampacity and the voltage drop. Okay? But for each of these 5 elements, there are current and horsepower considerations we need to think about and be aware of. And the NEC spells out specific minimums and maximum currents and horsepowers for each of these different elements. So we'll step through these and give some more specifics. So first, the disconnect means, or disconnect switch, must be lockable unless we have a non-stationary or mobile motor. If we have an unmounted motor, as in it's not permanently fixed, we can move it. We can actually have a simple cord to unplug to be our disconnect means. But we do want our disconnect means to be rated, the horsepower rating to be greater than or equal to the motor horsepower times the service factor. We want the current rating of our disconnect to be greater than or equal to the full load current of the motor times 115%. Now, very important, the current full load current is based on the NEC table 430.48 and 430.50. Okay, we'll have these at the end of this presentation. I have those on this slide deck. But this full load current is not the nameplate current. It's the actual current specified on these tables. So this is our disconnect means. Then we have our short circuit protection. And if we have a time delay fuse, if we use a fuse to do our short circuit protection, the rating of that fuse must be greater than or equal to 115% of the full load current or less than or equal to 175%. Okay, it has to be within that range of the full load current. If we're using an inverse time circuit breaker, the range is 115% of full load current or 250% full load current. Once again, current full load current is based on these 2 tables, NEC, when we're talking about the circuit breakers or a fuse, not the nameplate of the motor. So we look at motor controllers. This is the thing that turns the motor on and off. And the term operator is a fancy word for switch. So these have to be individually per motor. So we have an individual contactors per motor. Clearly marked switches or operators that say start, stop, forward, reverse, etc. The rating of the horsepower must be motor horsepower times the service factor. Current rating has to be 115% of the full load current. And like before, full load current is based on the tables at the end of this slide presentation. Motor overload protection, the overload relays or heaters, individual overloads per motor. Now this does not mean that there's one overload. This means for a 3-phase motor. If we have a 3-phase motor, we have 3 combined overloads as one element, one device, one per phase, but it's a single device that's providing protection for each phase of that motor. Okay. We need the current rating if the motor has a service factor less than or greater than or equal to 115%, as in 1.15. We need the current rating of our overload to be less than or equal to 125% of full load current. If our service factor of our motor is less than 1.15, then our current rating of full load is 115% full load current. Here's an important thing to note. This motor overload protection is based on the motor nameplate full load current. A lot of times this will be full load amps on the nameplate, FLA. So when we look at the motor overload protection, we got to look at the nameplate of the motor. Last but not least, our motor circuit conductors, our wires. Now, there's two scenarios. We can either have one motor in our circuit, and if that's the case, we want our ampacity rating to be greater than or equal to 125% of our full load current. So if our full load current is 100 amps, we need to assume that we need to find a wire that's rated for 125% amps. Sorry, 125 amps. If there are multiple motors in our circuit, okay, now there's more than one, the way we calculate ampacity is we say, let's take the largest motor, let's get 125% of that full load current, let's add the sum of all the other motor current, full load currents. Put those two together, that's our ampacity. And we look for a wire or a conductor at that ampacity rating. Okay, so two scenarios, a single motor versus more than one motor. Most often, and on the homework, we're going to deal with the single motor application. We need that ampacity to be 125% of the full load current. Now, we also want to make sure that we have a 2% minimum voltage drop. Okay, we can look at those tables in Chapter 5 for these. And once again, the full load current is based on the tables at the end of this chapter, not the nameplate, when we talk about conductors. So let's do a quick recap. We have the horsepower rating of our disconnect and our contactors need to be greater than or equal to the motor horsepower times the service factor of that motor. And the current rating needs to be 115% of the full load current of the motor. Our short circuit protection, if we're using fuses, has to be anywhere from 115% to 175% of the full load current of that motor, whereas circuit breakers are 115% to 250% full load current. And if we're talking about our conductors, right, a single motor greater than or equal to 125% of the full load current versus more than one motor is where we do the combine the largest motor, 125% current, full load current, plus all the other motors' full load currents. And last but not least, our overload relays. If our service factor of our motor is equal to or greater than 1.15, then our full load current times 125% is the rating we need to use, versus the other scenario where it's only 115% of full load current. When we talk about our relays, overload relays, these are based off of the motor nameplate. Okay? So we look at the motor nameplate. When we look at that, all other current and horsepower values look at the tables. Okay? Now, one point of clarification. In addition to the conductors, right? The conductors are just the things that we add to connect all these components, right? When we look at disconnect switch, fuse circuit breaker, contactor, overload, those things need to be satisfied. That doesn't mean we have to have 4 separate pieces of equipment to do each of those things. There are products that we can buy that will satisfy 2 or 3 of these things at once in one product. Okay? So companies are saying, buy our part, it's going to give you a disconnect switch and a fuse circuit breaker, and guess what? Even it allows you to turn the motor on and off. And so right there with one device you can cover 3 of those elements. So that's the game that some companies are going to play, and that's the game we can play. We can go out and find parts that satisfy multiple of these requirements. We still have to follow these current and horsepower rating guidelines, though. So here are the two tables. For single phase. So single phase motors, we have our horsepower ratings along the left side and our voltage ratings along the columns here. So for a 1 horsepower motor at 230, we are looking at 8 amps full load current. If we have a 230 5 horsepower 3-phase motor, we're looking at 15.2 full load current amps. So that's how we interpret these tables. We start at our horsepower, we go, what horsepower do we have? What voltage do we have? That number there then, 130, is our full load current. These numbers are different possibly than the nameplate. These are the numbers we need to use for most of those elements, those devices, when we start looking at what currents we need and what horsepowers we need. Just another clarification, the single phase table is actually reproduced in your textbook. So with that, we're going to stop this video presentation. We'll pick it back up in another one, and I'll show you some of the web links that will help you with your homework. Good luck.